Everybody, welcome back. So what we're looking at today is something actually I'm pretty excited to show you in class. Um, it's one of the first real sorts of tests as to whether or not light behaves as a wave, and one of the first conclusive pieces of evidence that it does. So I'm pretty excited to show you this actual phenomenon in class tomorrow. For right now, I'll have to go over the explanation with you. Um, and I'm also kind of excited just because, I mean, it's got the name Young in it, and so that's always cool. But it has to do with this guy named Thomas Young, late 1700s, early 1800s, and he worked with something called the double slit. And so basically, he was interested in two source interference, so like we talked about last time. So he knew exactly or how double source interference works. So if he had two sources of waves and then he put them beside each other and let them interfere with each other, what sort of pattern he would expect. And so he experimented with this. What he did is he actually put two very narrow slits on a card and put them in the sunlight. And then he let the light hit the card and he looked at what was projected onto a screen and looked at the pattern that came through the card and was excited to see what actually came out. Because again, if he saw the traditional interference pattern he got from water, that would be good evidence that light behaved as a wave, and if it didn't, that would again not be evidence for it, and he'd have to go back to the drawing board and see another sort of experiment to see if it behaved as a wave or not. Um, and so let me jump right to sort of what he did observe. And so you probably know already what we did observe because I'm talking about it, it's exciting. And this is sort of the pattern he observed. And so there is your sort of interference pattern. It's a little different than what we saw yesterday, just because now we're looking at a sort of static representation of a changing interference pattern. Um, so instead of seeing a wave bob up and down, what we're seeing is light. So the difference being, let's see if I can make this any bigger here. In the dark bands, so the spots where there isn't any light, like in here, that would be a region where the waves were interfering destructively, and the waves would have zero amplitude all the time. And the bright bands, the amplitudes would be going up and down quite rapidly, and you'd be having this constructive interference. And so the bright bands would be constructive interference. The dark bands, or dark fringes, he called them, would be destructive interference. And so this would actually then be good conclusive evidence that light in this case is behaving as a wave. And if we took a look at a graph of sort of what the intensity looked like over the position, we see this, again, traditional sort of interference pattern. We get really strong interference, constructive interference here in the middle. We'd have destructive interference to the side, but then you'd also be getting constructive interference at regular intervals away from this other point. Um, and so you'd be calling this, we call this a central maximum. We have other maxima towards the side, and we also have minima everywhere that the light intensity is near zero, or at least a minimum. And so again, this is pretty exciting because this is pretty conclusive evidence the light behaves as a wave in this experiment. And so you can see this is just like we talked about last time with water waves, that the light comes in and it's being diffracted by these slits, and then we're having these two sources that are interfering with each other, producing interference patterns. And so what we're going to look at today then is just kind of how can we mathematically model this. And luckily we've done most of the heavy lifting already last time, so we don't have to go through a lot of the calculations again. We're just going to kind of look at them in a different way and apply these things to light and see what we come up with. But again, this did take a long time for scientists to do this. And so the obvious question might be, why did this take so long? Um, if all we had to do was repeat what happened with water waves and do it with light, how come scientists before Thomas Young didn't discover this? And so I've got a quick question here. Um, could you just repeat Young's experiment with just two regular light bulbs, like a traditional incandescent bulb, and put them very close together instead of two slits? Would you expect an interference pattern? So what I want you to do again is think about this for a second, pause the video, and tell me, do you think you would see an interference pattern um, with just two regular bulbs close together as opposed to two slits? And I want you to tell me, first of all, would you, and then explain what you've told me. So pause the video. When you think you got an answer, start it up again. All right, so hopefully you've got an answer for me. And again, you just using some logic, you should probably guess the answer is no. Otherwise, this would have been discovered a long time ago. So the short answer here is no. You don't see this sort of phenomenon with just two incandescent bulbs very close together. And there's a couple really important reasons. Um, hopefully you got some of these. One, probably most importantly, we need very close distances here. Because the wavelength of light is very small, wavelengths are very small, we actually have to deal with very, very close together distances. So these slits need to be very close together. These sources need to be very close together because remember we talked about it the other day, that in order for diffraction to happen, we have to have these sources very close together. So that's probably one really sort of important one. And the other one that's maybe less obvious is these sources need to be in phase. And what the heck does that mean? Well, that means that when one light bulb or one source has its amplitude going up, the other light source has to have its amplitude going up as well. And really the only way to guarantee that is to make sure the light is coming from the same source. And we do that by using two slits as opposed to two actual different light bulbs. So the reason this wasn't discovered a whole lot long ago or longer before Young came around was because you need very close distances. So you can't just use two light bulbs close together, and two, you need to have these sources in phase. So those sorts of two big differences. All right, so now that we've got that under our belt, as I said, our kind of goal today is to come up with a mathematical relationship to try and predict where these bright and dark fringes are. And we'll do that by revisiting where we left off with water waves. So we went through this last time, and hopefully you're okay with this. And we determined that anywhere on this nodal line at this point Pn, we know that this condition needs to be satisfied. The difference in path for a wave traveling from source 1 compared to source 2 has to be half a wavelength at a step. So we said anywhere along this nodal line, or any nodal line, in fact, the wavelengths have to be half a wavelength, or 3/2, or 5/2, or 7/2 out a step, and they have to then satisfy this relationship. But what we're going to do today is we're going to say, okay, let's imagine we're really, really, really far away. And we can make that assumption for light because what we're talking about is these slits being very close together and our wavelengths being very small. Because again, light is on the order of nanometers for their wavelengths, so very small. And these slits are often going to be millimeters or less than millimeters apart. So we can usually make that assumption pretty safely. And so we're going to do that. And so if we do make that assumption, that we can say that a light or a wave leaving source 1 is parallel or close enough to parallel as a light source leaving, or a wave leaving light source 2. And so that means the path difference, this Pn S1 minus Pn S2, is really just this distance here. Because eventually, again, if these waves go off to infinity, they'd meet up at some point, Pn, that this is the only extra distance that one wave has traveled, this distance right here. And so this is the only real distance we need to care about. So what we're going to say is we're going to make that assumption and say this is our path difference. We're going to call it AS1. And so just looking at this triangle, AS1, we can just write it as this. So the path difference is given by AS1, and we can just use trig to write the sine of this angle, theta n, as this expression here. And then we can rewrite this expression we got last time just as this guy here. And so what does this expression mean? Well, this means in order to locate a dark fringe, it has to satisfy this expression. This angle has to match now. And again, this makes it easier for us because we're often dealing with very large distances. We're not going to be measuring things nanometers away from a screen, so we're okay to use this. Um, and we could actually go through, if you wanted to, and repeat the same process to go with bright spots. I'm not going to go through it, but it's pretty much the same sort of derivation, but we end up with a slightly different um, expression. But you can hopefully see the parallels here. And this will tell us where we can find our bright spots. So before we move on, let's just maybe make sure we're clear with what these expressions mean. And so that's what I'm going to do here for you. So these are our two expressions. These are our two sort of big ones for a double slit. And first of all, let's figure out what the heck these terms are talking about. So of course, lambda, that should be easy. That's the wavelength of light we're dealing with. So if we're dealing with red, we're in the order of like 600, 700 nanometers. We're dealing with blue, it's like 400 nanometers. This would even work with spectra or colors of light that are invisible to our eyes, so ultraviolet or infrared or gamma rays or any other light you'd care about. D will be the separation of the slits. Now the part that some people get a little confused about is what the heck do N and M represent? So again, we did similar stuff in grade 11. We did sound when we talked about resonance. But for this one, what we're going to talk about is N and M. N is the order of the minima. And minima, again, means dark fringe. Um, and so this is which sort of dark fringe is it? And we're going to count from the central maximum. So basically what we're seeing is if this is the setup for your double slit experiment. So here's the slits and here's the screen. Straight across from the slits, so like that perpendicular bisector, you're going to see a bright spot. So right in the center, you're going to see a bright fringe. And all our minimums are going to be counted from that bright fringe. So this one right here, this would be n equals 1 because it's the first minima away from the bright fringe. This will be n equals 2. This would be n equals 3. And don't forget, this is actually completely symmetrical, so this would also be n equals 1. This would also be n equals 2. And this would also be n equals 3, and it continues on and on and on. And so we're going to count from the central maxima. So then n is going to be either 1, 2, 3, 4, those natural counting numbers. M, if we're using this expression up here for the maxima, this again is going to be counting from that central fringe, that central bright fringe. But the difference with this one is we're going to start at 0, just because the central point, so straight across from the slits, actually is a bright fringe. So we're still going to count from the central maximum. But the first one, or like I guess the 0th order, is a bright fringe because how far away are we from the bright fringe when we're here? Well, we're 0 from it. So m equals 0. And then our first bright fringe away from it will be n equals 1. And the next one will be m equals 2, and so on and so on and so on. And all theta is just what is that angle. So from that that perpendicular bisector, or from that central maximum, what is that angle to determine where that other dark or bright fringe is. And again, just to keep these things straight, I normally use the kind of trick to remember which one is which. M is maxima, and N, well, that doesn't quite fit with dark, but you can use it as like N is nothing, or not much. So M would be maxima, N is nothing. So this is how I remember which one is which. And so we can actually go through and just figure out where am I going to see these bright and dark fringes. All right, so let's go through and do a couple examples here and make sure everyone's good with what we're talking about here. So here's the first one. So we're doing a double slit experiment, and the third order minimum is seen at 0.30 degrees away from the central maximum during this experiment. And the slits during this experiment are 0.35 millimeters apart, and I want to know what is the wavelength of the light being used. So the first question we should probably be asking ourselves is, okay, we're dealing with minimums, or minima, I guess. So we know we should be dealing with the minimum sort of expression, which is this guy here. And then we have to start picking stuff out. Well, we know we're dealing with the third order minimum. So that's our n equals 3 case. And then we've got 0.30 degrees, and we've got our slit separation, and we're looking for lambda. So kind of our givens required analysis sort of section here. This is what I know. And now it's just a simple matter of shoving stuff in, rearranging for theta. And again, I'll leave that to you, but what I'm getting is 733 nanometers, or 10 to the minus 9 meters, which, if you're interested, is actually a nice red color. Hence my selection of pen. Look at that, I'm awesome. So we know that this is actually a red laser. And this is kind of neat. We can actually use this sort of idea to determine what color light is. Um, or you can actually then use this idea to break light up into different colors. Um, and we'll talk more about the sort of breaking light up when we do diffraction gratings, which is something kind of neat. But you've seen these already. We've talked about spectra, so we use them to look at different colors of light to break it up into um, spectra. So you might have done this in chemistry as well, if you looked at different elements and looked at what kind of colors they give off. But anyways, we'll get to that. All right, so there's the first example. The next example we've got, I've got a blue laser now. That's kind of fun. There's the wavelength of the blue laser, and I'm shining it on a set of double slits. There's the separation of the slits, and I want to know how far away from the central maximum will I need to look in order to find the fourth order maximum if the screen is 12 meters away from the slits. So what is this question asking me for? Well, we know we're dealing with maxima, so we're dealing with the maxima expression here. So there it is there. We're dealing with m equals 4 because it's the fourth order maximum. Notice again, we don't have to worry about that 0 there because we're talking about the fourth order maximum, so that is m equals 4. M equals 0 would be the 0th order maximum. D again is the separation of the slits. Lambda is the wavelength of the laser involved, or light involved. In this case, it's 460 nanometers. And I want to know the distance involved. Now the problem here is there is no distance in our expression. Seem to be at an impasse. But luckily again, if we remember what the heck this theta actually represents, we're not at a total loss because we really don't, we're not at a complete loss because we actually know where we're going. So here's my kind of schematic diagram what's going on. So here's the screen, here's the slits, here's the laser. And so we have the light coming in, it's being diffracted, and then we're seeing the nice diffraction pattern up here. And here is my 0th order. So right here, there's the m equals 0 case right there. And up here, we have 1, 2, 3, 4. So there's my m equals 4 case. And I want to know what is how far from the central maximum, so how far from this guy, would the fourth order maximum be. So what is this here? Oops, let's try that again. What would this distance be here? Your textbook calls that distance x4. And I'm good with that definite, or that sort of terminology as well, so let's stick with that. So I want to know what the heck is x4. And we say, okay, well, I can't find x4 at this expression, but I can find theta 4. And so that theta 4 would just be this angle here. So let's find theta 4. And again, I'll leave it to you to find, but when I find theta 4, I'm finding a pretty small angle, but I'm finding theta 4 is actually then 0.234277 degrees, so quite a small angle. But then I can actually just use my simple trig ratios because I've got this idea here. So there's my theta. I know this is 12 meters, and I want to know x4. So again, that's just your trig ratios. So I'm getting a distance of x4, or the distance between that is 4.9 centimeters. So I hope you can appreciate how small that distance is. So even with these high frequency or low wavelength lights and these pretty small separation slits, we don't see a huge separation between these maxima and minima. And so this is one of the reasons why it took people like Thomas Young so long to actually get some good evidence here for light behaving as a wave. So again, I don't think today should have been too bad if yesterday's stuff was okay, just because we're kind of piggybacking on the heavy lifting we did then. But of course, if you're having difficulty, let me know, and we'll talk about the stuff in class tomorrow. I'm pretty excited to show you the actual stuff with these in class and show you how we can change some of the stuff up and make some observation of this. All right, so we'll see you in class tomorrow, and have a good night.